Hello everyone, welcome to this video. In this video, we shall continue to discuss some of the facts related to Riemann criterion for integrability. So already we have discussed one of the fact in the previous video. So now the second one is let f be a bounded real valued function defined on closed interval a comma b and alpha be any monotonically increasing function on the closed interval a comma b. If UPF alpha minus LPF alpha is less than epsilon for some partition P with respect to some epsilon positive, and SI and TI are any arbitrary points of the closed interval xi minus 1 xi, then we have to prove summation f of Si minus f of Ti into delta alpha I is less than epsilon. So this is what we have to prove. It is actually a mathematical, purely calculative proof. So there is no much theory. So using this inequality UPF alpha minus LPF alpha, we have to prove. So summation modulus of f of Si minus f of Ti into delta alpha I n from 1 to n is less than epsilon. So where we have taken the partition P as x0, x1, xn minus 1, xn. So now we shall prove it. So given UPF alpha minus LPF alpha is less than epsilon for some partition P of closed interval a comma b and with respect to some epsilon positive. So this is what they have given. Now take the partition P as x0, x1, x2, xn minus 1, xn. And as we have discussed many times, any partition of a closed interval a comma b divides that closed interval into subintervals. So here also, as P contains n plus 1 points, P divides the closed interval a comma b into n subintervals. Those are x0 to x1, x1 to x2, so on xn minus 1 to xn. Right now, over each closed interval, so this is actually the situation. So this is A, which is x naught, and xn is nothing but b. So in between there are points x1, x2, so on, xn minus 1. So the closed interval a comma b is divided into subintervals, right? So now for each closed interval define min infimum and supremum, right? So define mi to be the infimum of all f of x as x varies over some closed interval xi minus 1 xi, and capital Mi to be supremum of all f of x as x varies over the closed interval xi minus 1 xi, and I is true for 1, 2 up to n. That is, if I put I is equal to 1, so it will be the closed interval x0 to x1. If I put I is equal to 2, it will be x1, x2. So like this, I have defined infimum and supremum for each of the subintervals. Now, for any general ith interval, consider any two arbitrary points. Si and Ti be any two arbitrary points of the ith closed interval, subinterval, xi minus 1, xi. So as these two are points of this closed interval, so if I consider those corresponding function values, so for all points in this closed interval, so the function values have infimum and supremum, right? For all x varying over this closed interval, so these f of x's have infimum, that is greatest lower bound, and it is mi. And as x varies over this closed interval, so these f of x values have supremum, that is least upper bound, which is capital Mi. So now Si and Ti are any two particular points in this closed interval. So corresponding to which, if we consider the function values, so these two will be bounded below by Mi, as Mi is the infimum, and these two will be bounded above by capital Mi, as capital Mi is supremum, that is least upper bound. So now the situation is like this. So suppose this is the function f of x. So if this is the closed interval xi minus 1 xi, so corresponding to this, so suppose this is mi, so it will be the infimum or minimum value. So suppose this is maximum, capital Mi. So in this in this range only you will get f of si and f of ti, f of ti. So both are in between mi and capital Mi. So suppose this is f of si, this is f of ti. So this is capital Mi, this is small mi. So in this range only we will get all the function values for the points x varying over xi minus 1 xi. Now take the difference of these two. So we don't know whichever is smaller or bigger. So f of si could be smaller or f of ti could be smaller. We don't know. But take the difference. So take the absolute value of the difference. That is, take the difference of bigger one minus smaller one. So whichever is bigger, so that minus smaller one. So that difference will be this much. So this will be the difference modulus of f of si minus f of ti. Now, if I consider this difference, that is mi minus mi, bigger, big mi minus small mi. So this difference will be greater than or equal to the difference f of si minus f of ti. So, and it is also obvious, you can observe here only, as these two members are in between mi and capital Mi. So if I take their difference, absolute value, their difference, it will be less than or equal to capital Mi minus small mi. So that only I have explained using the graph. So if this is the graph, suppose this is the infimum Mi and this is the suppose supremum capital Mi. So all the function values will be in this range only. So suppose this is f of ti, this is f of si, then so their difference, what it will be, just this much, it will be this much. So this is the difference of f of si and f of ti. Take its absolute value. So this will be the difference. Now observe, compare this difference and this difference. So yeah, mi minus small mi will be greater than or equal to the difference f of si minus f of ti. So it is obvious. Now, to this inequality, multiply delta alpha I on both sides. As for each I, delta alpha I is defined to be alpha of xi minus alpha of xi minus 1. So as alpha is a monotonically increasing function and xi is greater than or equal to xi minus 1, actually greater than. So delta alpha will be non-negative. We know that. So multiplying a non-negative quantity on both sides will retain the inequality. So inequality remains the same on multiplying delta alpha. So which is true for every I. So for any I, this value, the left hand side value is always less than or equal to the corresponding right hand side value. So this is true for every I. If you put I is equal to 1, so corresponding to I is equal to 1, the left hand side will be less than or equal to the right hand side value corresponding to I is equal to 1. So sum up all the left hand side values and the right hand side values. So this sum will be less than or equal to this sum. So as all these numbers are strictly less than or equal to these numbers, so if you sum up these, it will be less than or equal to the sum of all these numbers. Next, on the right hand side, just we shall simplify it. So multiply delta alpha inside, it will be capital Mi into delta alpha minus small mi into delta alpha. So split the summation with respect to the two terms. So summation capital Mi into delta alpha minus summation small mi into delta alpha I. And according to our definition, the first summation is nothing but the upper Riemann Stieltje sum UPF alpha minus the second term is what? It is the lower Riemann Stieltje sum LPF alpha. But according to our hypothesis, it is less than epsilon. So what we started with? So we started with this one. So summation f of si minus f of ti into delta alpha I running from 1 to n. So this we got it to be less than epsilon. So which completes the proof. So it is purely so calculative. So just purely mathematical steps everywhere. Just go through it. Next fact, so which is taken as the theorem C. So let f be a bounded real valued function defined on closed interval a comma b, and alpha be a monotonically increasing function on the closed interval a comma b. If f is a Riemann Stieltje integrable function on closed interval a comma b, and UPF alpha minus LPF alpha is less than epsilon for some partition and for some epsilon, then modulus of summation f of ti delta alpha I minus the Riemann Stieltje integral of f over the closed interval a comma b with respect to alpha is less than epsilon. So this modulus is less than epsilon, which we have to prove. Where what are TIs? So where P is taken as the partition x0, x1, xn, so that it divides the closed interval into n subintervals x0, x1, x1, x2, so on, where xi minus 1 xi is the general ith closed interval, ith closed subinterval. So now where ti is any arbitrary point of it. So for any ti of the closed interval xi minus 1 xi, this inequality holds, right? So proof for any I. So already we have considered the partition P. So this partition P of closed interval a comma b divides the closed interval into subintervals. So x0 to x1, x1 to x2, so on xn minus 1 to xn. Now on these each closed intervals, so define infimum and supremum as we done in the previous theorem. Do the same thing. So for each subinterval xi minus 1 xi, so define the infimum and supremum. Let mi be infimum of all f of x's as x varies over the closed interval xi minus 1 xi, and capital Mi to be the supremum of all f of x as x varies over the closed interval xi minus 1 xi. Now, if ti is any arbitrary point of the ith closed interval xi minus 1 xi, then its function value has both infimum and supremum, right? As x varies over this closed interval, all the f of x values have the infimum and they have also the supremum. So infimum means what? It is the greatest lower bound, and supremum means it is the least upper bound. So if ti is any point in this closed interval, the corresponding function value f of ti will be greater than or equal to small mi, as mi is the greatest lower bound, and it will be less than or equal to capital Mi, as capital Mi is supremum, that is least upper bound. Now to this inequality, multiply delta alpha I, as once again delta alpha I is non-negative. So on multiplying delta alpha I to this inequality, the inequality remains the same. So mi delta alpha I less than or equal to f of ti delta alpha I less than or equal to capital Mi into delta alpha I. So which is true for every I. So for every I, so this term is less than or equal to this term, which is less than or equal to this term. So if we take the sum of all these first terms, that sum will be less than or equal to the sum of all second terms, less than or equal to sum of all the third terms. So the first summation is nothing but the lower Riemann Stieltje sum LPF alpha less than or equal to summation f of ti delta alpha I less than or equal to the third summation is nothing but the upper Riemann Stieltje sum, which is UPF alpha. So call this as equation 1. And previously, while discussing the relation between the lower Riemann-Stieltje integral and the upper Riemann-Stieltje integral, we have observed that the Riemann-Stieltje integral of f with respect to alpha over the closed interval a comma b always lies in between the lower Riemann-Stieltje sum and the upper Riemann-Stieltje sum. So this is true for actually for any partition. So for any partition P, the Riemann-Stieltje value integral value always lies in between the lower Riemann Stieltje sum and the upper Riemann Stieltje sum. So in particular, the partition which we have considered here. So in the given hypothesis, what they have given, this is true for some partition. So as this condition is true for all the partitions, in particular, this will be true for the given partition also. So call this as equation 2. So now observe, so this value and this value, both are in between LPF alpha and UPF alpha. So once again, the same thing on the real line, as all these are real numbers, just I'll show graphically. So LPF alpha will be here, UPF alpha will be here. So these are lower and upper bounds. So in this range only both numbers are there. I don't know which is smaller and bigger, but both are in between LPF alpha and UPF alpha, right? So just I'll if I assume, so summation is smaller and the Riemann Stieltje integral is bigger, suppose. So like this. So if I take the difference, so this minus this means, so this will be the difference. So this length of this line joining these 2 points will be nothing but the difference of these two numbers. So and this difference will be obviously less than or equal to this difference, that is from UPF alpha to LPF alpha. So difference between these two numbers is always less than or equal to difference between these two numbers. So that is what we have done here. So take the absolute value of the difference. So that is take the difference from larger, subtract from larger to smaller. So subtract the smaller from the larger one. So the absolute value will be less than or equal to, so UPF alpha minus LPF alpha. So this difference is nothing but this one, this one, and UPF alpha minus LPF alpha means this one. So obviously you can observe, so this difference is less than or equal to this difference. So but by the given hypothesis, UPF alpha minus LPF alpha is less than epsilon. So the given or the modulus which we have considered is less than epsilon, and which is the required result. So these are the some facts related to Riemann criterion for integrability. So based on the result, Riemann criterion for integrability. So these are the some observations, theorem A, which is in the previous video, theorem B and theorem C of this video. So these are some observations which will be useful in some further results.